Okay, so then, yeah, first of all, thanks to Nikolai for inviting me for this seminar. It's very nice to be here and see a lot of friends, even so it's just an online seminar.
Wolfram, excuse me, you are not really here. You're overseas.
Yeah, that's true, but somehow I can see you at least. Yeah, okay. So I hope there are not too many duplications with the talk Robert gave at the seminar, because this is actually joint work and part of his PhD, and also I explained a few parts already in the seminar last time. But anyway, so duplications don't hurt too much, I guess. So I want to talk about this old theorem by Berger and Coburn and some generalization, correspondence theory and characterizations of the Toeplitz algebra. So there will be some old stuff and maybe some small new things, and some new perspective, I hope, on some theorems. So this is my my outline. I want to go through some notations and basic facts, but I think in this seminar I can do this very quickly. I don't have to explain what is a Toeplitz operator. And then I start with this Berger-Coburn theorem, which gives the criterion on the boundedness of a Toeplitz operator with in general unbounded symbol. And here I want to give a new proof which generalizes the theorem from the L2 setting to the LP setting, so to say, where P is not equal to 2, and it slightly generalizes also the result. And then for the rest of the talk, I want to talk about the Toeplitz algebra, which is the full Toeplitz algebra on the Fock space, generated by all Toeplitz operators with bounded measurable symbols. And here all symbols will be bounded. In part 1, they may be unbounded, but I will use a few of these, or actually one inequality which comes from here, which also has some application in this part. So there's some connection between these two parts. And then I want to explain a bit what is quantum harmonic analysis and the correspondence principle, and how to get several old theorems on Toeplitz operators and some new theorems by this principle. And I think this is a very nice framework to look at Toeplitz operators in the setting of the Fock space. So everything will be here in the Fock space setting. Okay, so also if there are questions, you can just interrupt me. Stop me.
Не, ну я пронесу сейчас.
Да, пронеси. А сядь там так, чтобы я все...
Сережа, выключи микрофон.
Okay. Okay, so this is on the notation and basic facts. So here I consider only Cn, n space, and I consider a family of Gaussian measures on this, the standard family, which is denoted by d mu t. T is a parameter bigger than 0. You may think of this as a time parameter. And here we have this, this Gaussian weight, and it's normalized to 1. And then I consider p between 1 and infinity, and some parameter t bigger than 0. And I look at these LP spaces, LP of Cn with respect to this measure. And important here in this parameter of the measure, actually this p, this exponent p appears, which is a bit unusual, but anyway. And then the p Fock space, which is denoted by ftp, is just the intersection, as usual, of the holomorphic functions with the LP space, this LP space here. So that gives a family of spaces parameterized by t. And now I can also define the same thing for p equal infinity. Here I look at a measurable function from Cn to C. And then I look at this subnorm here, at this essential supremum of the function multiplied with this Gaussian factor here, which is actually the square root of the density function here. And then L infinity t will be just the space of all measurable function, which have a finite norm here of that type. And then F infinity t will be the space of holomorphic functions in that space. So functions in that space here can be rather unbounded, and they contain certainly all polynomials or other holomorphic functions. Okay, and then there are some well-known facts. If p equal 2, then we are in the classical situation of just a Fock space. That's a reproducing kernel Hilbert space. And here's the reproducing kernel. You all know it's just that exponential here. It depends on t. That was the parameter in the measure. And in particular, we have the orthogonal projection from this L2 space to the Fock space, which I denote by pt. And it's just that integral operator here against the reproducing kernel with respect to that measure. So that's all very standard. And now if I define these LP spaces here in the way I did, so in particular, if in the measure I have this P dependence, and P can be in between 1 and infinity, then the observation is that that projection here is still a bounded projection from LTP to the P Fock space. So that is a nice thing. And now I can pass to Toeplitz operators. They are defined on these P Fock spaces for P between 1 and infinity. And this is my notation here as usual, and they are just compression of multiplication operators. And this projection P is some measurable function. And important here in the first part, P might be also an unbounded function. Might be an unbounded function. So these are in general unbounded operators. And I look at these operators on the domain, which is written here. D, T, F, T consists of all functions H, such that the product F times H is in the LP space again. Okay, and then this is some kind of quantization. So we take a symbol and we turn this into an operator. And then we have this kind of inverse quantization, which takes an operator and turns it into a function, which is called Berger transform. And let me only write it for P equal 2, but you all know. So if you have a bounded operator on the 2 Fock space, then this function here, where KCT is the normalized reproducing kernel, gives you a function which is the Berger transform. And in particular, if I take a Toeplitz operator with a symbol F, and the symbol can be unbounded, but we need that these products here of F times this normalized kernel are still in this L2 space for all set. So under this condition here, then we can look at the Berger transform of the Toeplitz operator, which is usually denoted in this way here. And it turns out to be just the heat transform, which is the solution of the heat equation at time t, let's say, with initial data f, and that integral transform here. Okay, these are all well-known things. And now the question, one basic question in this setting, of course, is when is a Toeplitz operator on the Fock space with an unbounded symbol, when is it a bounded operator? And there's a result by Berger and Coburn in that direction, and it tells you the following. So if you have a symbol f, which is an L2 function, here, and then you can consider the Toeplitz operator with that symbol on the 2 Fock space. So P equal 2 here. Then you have the following 2 estimates. So there's a constant CS, where S is some number between 2t and t half, such that the operator norm of the Toeplitz operator is bigger or equal the subnorm of the heat transform of that function f at some time s. So for large s, large meaning s bigger than t half, the operator norm dominates the subnorm of the heat transform. And for small s, which means s is smaller than t half, t that parameter in the Gaussian measure, you have the reversed inequality. So then the operator norm is bounded by the subnorm of the heat transform. So what typically can happen is that you start with a symbol f, which is maybe very unbounded and oscillates a lot, and then you look at the heat transform of this, and if time s runs, then at some time this may become a bounded function, and then it stays bound for all later times. So that may happen. So these are CS, capital CS and small cs are some universal constant which depend on these parameters S, T, and N, and one can give some estimates on this. Okay, this is
one question to that. If you just consider your heat transform, Berger transform, applied to a function is the same as applied for Toeplitz operator.
Yes.
And if you just do normal scalar product, that you have normalized kernels, and it will always measured by norm of Toeplitz operator.
Yes, yes, that's true. If T is if S is equal to T.
Yes, if F is equal
to T.
Yeah,
but
sure,
here what you do is you change S. You change S.
Okay,
so that S does not fit very well to the inner product of the T space.
Yeah, sure.
So what happens is, for example, you may have a function which is very unbounded and oscillates a lot. And then the heat transform of that time at small times, somehow in some sense still close to the function. So it's still unbounded. But then if time runs and you think of the heat flow, then it may happen that just due to the oscillation, it becomes eventually a bounded function. That happens. Then it stays bounded forever. So that such things may happen. Okay, so I want to discuss a bit the second inequality here. If you look at the original paper by Berger and Coburn, what they did here, they want to prove boundedness of a Toeplitz operator, and they look at the Barkman isometry between the 2-Fock space and the L2 space. And then they change this Toeplitz operator into a Weil pseudo-differential operator, and they look what happens to the symbol, and then they prove the boundedness of this Weil pseudo-differential operator by Calderon-Vaillancourt theorem. So this is their strategy. It's a bit complicated, but it leads to this inequality here. So, but in fact, it's just, this only works if p equal 2, and it's a bit complicated. And here I want to explain that that actually is just a consequence of the Schur test. So I want to give a simple proof of this second inequality. And here's the idea. So we look at the off-diagonal extension of the heat transform, or what I call the Berger transform. So I replace here in the Berger transform the second variable z by a w, and then I get this function here. And what is well known that you can rewrite the Toeplitz operator as an integral operator where this function here actually appears. So it's part of the integral kernel. And this is the formula which you can check. This is the formula for the Toeplitz operator, where instead of f, you replace here, you put in here the heat transform f twiddle at time t. And now the idea is we can try to change this t to some s, some earlier parameter, smaller parameter, and see how these functions are somehow related. And so this is the idea. Now I want to look at different times here, and I want to relate these kernels for different parameters t here. And what helps us to do this is that the heat transform really has the semi-group property. That means this property, if I take the heat transform at time s, t, and then I go to time s, then this is just the heat transform at time t plus s. But that only works on the diagonal. So, but this semi-group property somehow translates also to off-diagonal values. And here's the formula. So the semi-group property of the heat transform, if you extend it to off-diagonal values here, then you get this type of formula here with some strange factor here in front. And now, if you assume that the heat transform at some time s, which is smaller than t, is bounded, then you can further try to estimate this inner product here by some integral estimates. And what you get out of this is this estimate which is written here. So you can bound the heat transform at time t, or the off-diagonal extension, by this value here, by this exponential times the subnorm of the heat transform at time s. And okay, the proof is you squeeze this out from the semi-group property and some analytic continuation argument, and then also you apply some integral estimate on this inner product here. So you see this factor here already appears here, and the second factor here with the minus sign comes from estimating actually this inner product here and using the boundedness of this function here. Okay, this is the important inequality, equality actually, and now you can look at the exponent here, and you observe that that is negative if and only if s is smaller t half, and that's the t half, or this border which appears in the Berger Coburn theory. Okay, and now we can prove the following. I just want to skip the statement. So if f is a function such that the heat transform at some time s, which is smaller than t half, is a bounded function, then we can look at this integral operator which is written here, and that was just the same expression as in the Toeplitz operator which I just showed you, but I may consider this not on the p-Fock space but on the whole LP space. So that integral operator maps from LTP to FTP, and under this condition here, under the boundedness of this for small s, that's a bounded operator. And we can estimate the operator norm by some constant c times the supremum norm of that heat transform here. And again, one can somehow calculate that constant here. And in particular, that means that if p is between 1 and infinity, then the Toeplitz operator, which coincides, or is just the restriction of this integral operator to fp, is also bounded, and you have the same norm inequality. So that theorem somehow extends the Berger Coburn theorem to p between 1 and infinity, also these non-reflexive cases. And it gives actually, the proof is actually rather simple. You just check it by using the inequality I just showed you in the case p equal 1 and p equal infinity by a direct calculation. That's rather easy. and then you use interpolation, a complex interpolation.
Wolfram, one question, please.
Yes.
This constant C does not depend on value of P, or depends?
Probably it depends on the value of P, but the behavior, what is interesting is the behavior if S approaches T half, and that cross does not depend on P.
Okay.
Okay, you can do the border cases and then you do complex interpolation. If you're not interested in P not equal to, only Hilbert space case, you can just directly use the Schur test together with the inequality I showed you, and it gives you the same result. Okay, so this will be useful also in the following. So there are a few remarks. One remark is that theorem holds if S is smaller than T half. So if S approaches T half, then this constant C in the norm estimate behaves like this, T over T half minus S. So it blows up of that rate here. And that leads to the question, what happens actually at the Borel case T equal 1/2? And there is some conjecture, I think, which is still open, saying that the Toeplitz operator might be bounded if and only if the heat transform is a bounded function at S equal T half. So that may or may not be true. One may look at more general cases, maybe at the boundedness of products of Toeplitz operators with unbounded symbols. That's also interesting. There's some work, for example, by Cho, Park, and Chu, where they do this for F analytic and Chi anti-analytic function, and they discuss the boundedness of this. To my knowledge, if you do the same thing for F anti-analytic and Chi analytic, then the question is more complicated, and I don't know the answer. Okay, these are a few remarks. So here's a positive result. So the boundedness of the Toeplitz operator for an unbounded symbol somehow is obtained by studying boundedness of the heat transform for different times. If you look at BMO functions, functions of bounded mean oscillation, this class contains also unbounded functions, but Crows is rather mild, maybe at infinity. But this restriction on the oscillation of the function causes that the heat transform of such a function is bounded for one t if and only if it is bounded for all t. So you somehow can control the boundedness of the heat transform backwards in time if you a priori put some oscillation condition on the function. And that allows you to improve actually the estimates, because you are allowed in the inequality to choose also S very close to, so you can choose S as wherever you want, smaller than T. And in particular, that tells you that in this case, for these symbols, this conjecture here is correct. So the operator, the Toeplitz operator with that type of symbol on the 2 Fock space is bounded if and only if the heat transform at time T half is bounded. That's true in that case. And I will use that theorem again for another purpose. Okay, so now let me come to the part 2, which is somehow a different topic. I want to give different characterizations of the Toeplitz algebra. And I want to start with a very old result by English from 1999, which was proved in the case where P equal 2, so in the Hilbert space setting. And he wants to characterize compactness of Toeplitz operators on the Fock space. And there already was the characterization by Exler and Cheng, I think, for Toeplitz operators on the Bergman space over the unit disk, and the result is more or less the same. So if you have a bounded operator on the Fock space, on the 2 Fock space, and if this is a finite sum of finite products of Toeplitz operators with essentially bounded symbols, then you have the following equivalence. The operator is compact if and only if the Berger transform vanishes at infinity. So compactness for this type of operator, you can read from the boundary or from the behavior of the Berger transform at infinity. So here I want to explain some first generalization of this result to some larger class of operators. And here's something you could do. And I only want to explain in the case T equal 1 and the Hilbert space setting P equal 2, but this is not such an essential restriction. So I choose a sequence of real numbers. So C0 is just 0, and then inductively I define Cn plus 1 is 1 over 4 times 1 minus Cn. And these numbers, this is a monotone increasing sequence of numbers, and they are all smaller than 1/2. You can check easily. And now I assign to each number, Cn, I assign a norm, which is this essential supremum, where this Cn appears here in this function, in this exponential above. And now these Cn's are increasing. So what I get is a family of spaces, H index Cn, which should be analytic functions on Cn, which have bounded Cn norm. And since this sequence is increasing, what we actually get is a scale of Banach spaces which are increasing, and H is the union of all of these. And since Cn always smaller than 1/2, that sits in the Fock space. That sits inside the Fock space. And now I look at the unitary while operators, which are some type of shift operators on the Fock space, with some multiplication by the normalized kernel, which makes that shift unitary. So I shift in direction Z. And then if I have an operator A acting on the Fock space, then by A index Z or alpha set of A, I will denote A conjugated by these unitary operators here. So that will be my notation in the following. And now I want to define an algebra, a certain algebra of operators acting on the Fock space.
Wolfram, wait a minute.
Yes?
This exactly the shift which will appear later on in quantum harmonic analysis.
Yes, on the operator side, yes. That's the shift of operators. Okay, so now I have this sequence of spaces, and these are somehow similar to a sequence of Sobolev spaces. If you now I want to look at operators acting on these spaces in a nice way, such as pseudo-differential operators act on the sequence on the scale of Sobolev spaces. So I say a bounded operator on the Fock space, which leaves this union of all these spaces Hn invariant. So that H was that union, or that union of spaces. I will say such operator acts uniformly continuous on this above scale. If for some index n1 in n, I find some index n2, which is larger or equal n1, some constant d, which is independent of z in C, such that for all f in this space of analytic functions Hn1, I have this inequality here. So somehow this operator acts from one of these spaces Hn1 to another space Hn2 in some uniform way, in the sense that it is uniform for all Z and Cn. So they act nicely on this scale of Banach spaces. And it's clear that that type of operators, they form an algebra. If I multiply two of them, then again, they will act nicely. And this space of operators which act on this scale of Banach spaces uniformly continuous, they are denoted by FL. So these are these operators, and they form an operator algebra. And then one can check that this is actually a star algebra. It contains all Toeplitz operators with bounded symbols. They all act nicely on that scale of Banach spaces. And the compactness characterization of English extends to that algebra. So if I have an operator in that algebra of operators acting uniformly continuous on that scale of Banach spaces, then that operator is compact if and only if the Berger transform vanishes at infinity, and that's actually larger, contains more operators than just finite sums of finite products of Toeplitz operators. So that's a first generalization. And then I can go a bit further. Now I want to consider just the case p equal 2, but also this is not essential here. And I can consider the C star algebra, which is generated by Toeplitz operators with bounded symbols. This is my notation. So C star of all Toeplitz operators with bounded symbols, that's the Toeplitz algebra. And then a further generalization of English result is a result by Joshua Israelowitz, myself in 2012, which says that an operator, a bounded operator on the 2 Fock space, is compact if and only if it is contained in the Toeplitz algebra, in this one here, and the Berger transform vanishes at infinity. Okay, so this is the result in the Hilbert space setting. Actually, this result generalizes to p Fock spaces if p is between 1 and infinity. Actually, it also generalizes if p equal infinity, but there's a problem if p equal 1, because in that case, the Toeplitz algebra does not contain necessarily all compact operators. Then one has to check.
Sorry, one question again.
Yes.
As far as I remember, that Suarez proved that it might be cases when Berezin transform vanishes at boundary, but operator does not belong to Toeplitz algebra, and so it does not compile. Do you have such example for the Fock space?
The Toeplitz, the Berezin transform vanishes at the boundary.
Yes.
But the operator does not
belong to the Toeplitz algebra?
Yeah, of course. There are very simple examples, just the reflection of the argument. So if you look at the operator, f of z goes to f of minus z. That's an example. It's unitary operator.
This was exactly the example in the Bergman space setting.
Yeah, this is also here the same thing. And actually, that operator has a distance 1 to all Toeplitz operators.
Yeah,
so it's it's far away from Toeplitz operator. Okay, so this generalizes also to this p-Fock space setting. And now there's the question, is there some relation between these two theorems? So the theorem for the Toeplitz algebra and for this algebra of operators acting uniformly continuous on the scale. And to answer this question, I want to mention another approach by Israelowitz, Mitkowski, and Wick in 2015. And they defined the notion of sufficiently localized operators. So they look at operators A, bounded operators on the two Fock space, and then they look at this kernel here, which I discussed before in this proof of the Berger Coburn theorem if A was the Toeplitz operator. And they look at this kernel here, the Berezin transform extended off diagonal, and they say an operator is sufficiently localized if this has a very good off-diagonal decay, meaning that is dominated by some constant c divided by 1 minus absolute value of z minus w, and this beta here should be bigger than 2n. It should be bigger than 2n. That comes somehow from an L1 condition on that function here. So if this decays nicely, if z and in this way here, then the operator is called sufficiently localized. And then they denote the set of sufficiently localized operators by A index SL. Okay, there's one remark. Here, let me go back. I assume that the operator A is bounded, and it fulfills this inequality. But in fact, if I have a mild condition on the adjoint of the operator, namely that the domain of the adjoint of this operator also contains all normalized kernels with z in C or Cn, here should be an n, then the boundedness of the operator here actually follows from that automatically. And now what one can do is one can take all the sufficiently localized operators with these nice kernels, and we look at the C-star algebra generated by this. That's a C-star subalgebra of all bounded operators on the two Fock space. And as I showed you already in the previous calculation, that a Toeplitz operator with bounded symbol certainly is sufficiently localized. So this here contains all Toeplitz operators. Since it's a C-star algebra, it contains also the full Toeplitz algebra. And I want to give you more examples of sufficiently localized operators which are not Toeplitz operators with bounded symbols. So for example, one noticed that an operator in this algebra FL of operators acting uniformly continuous on the scale of Banach spaces, they are also sufficiently localized. So this nice action on the scale is reflected by a good behavior of the kernel. So another example is this one. If you take a symbol in the space BMO of functions having bounded mean oscillation, that symbol could be an unbounded function. And if you look at the Toeplitz operator with that possibly unbounded symbol, then that operator could be still a bounded operator. And if that happens, then that operator is sufficiently localized.
But does not belong to Toeplitz operator algebra?
Yes, it does. In that case, it does. It's not clear for the moment, but it does. And here's the proof. It follows actually from the equality I showed you together with this with another result on the BMO. So I told you if S is some parameter between 0 and 1, here t is equal to 1, that's why. Then I have this equality between this kernel here, this off-diagonal extension of the Berezin transform at time t equal 1, here t equal 1, and t equal s. And then one checks that if I have a bounded function, then I can estimate these type of integrals here, this type of inner products here, by the subnorm of this function times this exponential factor. So I can apply this to this inner product here in case that function here is bounded. And that's what I do. Now, if I assume that the Toeplitz operator is bounded, but the symbol is in BMO, then from the Berger Coburn theorem, I know that the heat transform of that symbol at some time will be bounded. At some time t, it will be bounded. But I told you if the symbol is in BMO, then we have some backwards control of the boundedness of the heat transform. So if it's bounded at some time, it will be bounded at any time, at any earlier and any later time. So we know, we know that the heat transform actually is bounded for each time. It's immediately bounded once s is bigger than 0. And that allows us to use this inequality here across this strange border t-half. And that's what we do next. So we choose now s smaller than t-half, which is 1/2 in our case, which is now possible. And according to what I just told you, at this early time, this heat transform f tilde s is still a bounded function. But if I do this and I combine the two estimates, I get that estimate here. And if s is smaller than 1/2, then you see the exponent here is negative. It becomes negative. So this one has a very nice decay, even exponential decay. And that means the Toeplitz operator TF is sufficiently localized. And that tells me that I can actually reach compactness of that operator from the behavior of the Berger transform at infinity. Okay, so what is the relation between these sufficiently localized operators and the Toeplitz algebra? First, there was this result by Shah and Cheng, which extends this result by Engels and the generalization I told you actually to that C-star algebra generated by sufficiently localized operators. And it says an operator in the C-star algebra generated by sufficiently localized operators is compact if and only if the Berger transform vanishes at infinity. Okay. And that, together with the previous result, tells me that if I have a bounded operator on the 2-Fock space, which is, let's say, a finite sum of finite products of bounded Toeplitz operators with possibly unbounded symbols, but in the BMO space, then this operator still is compact if and only if the Berger transform vanishes to infinity. So under some, okay, you allow a bit of unboundedness, and this result still is true. Of course, this follows by the fact that these operators here are sufficiently localized, so they are inside this C-star algebra here. That's just a combination of the last two results. That actually was known for a single Toeplitz operator with BMO symbol. That's in some paper by Coburn and Lee, where they calculate that directly without using these relations. Okay, then there are another result by Shah, which is somehow surprising, and says that the Toeplitz algebra, so the C-star algebra generated by all Toeplitz operators in the case where p equal 2, is nothing than just the linear closure of the space of all Toeplitz operators with bounded symbols. So it's a lot smaller than one would expect. And also this Toeplitz algebra just coincides with the C-star algebra generated by sufficiently localized operators. So these are all the same things. And from this, we get another characterization of the Toeplitz algebra, namely the following. So if I take this algebra of operators which uniformly continuous act on the scale of Banach spaces, and I look at the norm closure of this, that's a C-star algebra. And again, what it is, it's just the Toeplitz algebra. So this norm closure also is the Toeplitz algebra. And the Toeplitz algebra is also the C-star algebra, which is generated by Toeplitz operators with BMO symbols when I assume that the corresponding operators are bounded. That's also the Toeplitz algebra. And that just easily follows from combining the previous results. So here's the simple proof. We already saw that this algebra of operators acting uniformly continuous on the scale contain all Toeplitz operators. It's with bounded symbols. It's a C-star algebra, so it contains the Toeplitz algebra. On the other hand, operators in this algebra are sufficiently localized. That one is a C-star algebra, so it contains the whole closure here. But by the Shah results, by Shah's result, that's just the Toeplitz algebra. So also you have the converse inclusion. And the other statement is the following. if we already have, we know that L infinity is in BMO. So certainly the Toeplitz algebra is contained in the C-star algebra generated by Toeplitz operators with BMO symbols, TF bounded. And I just told you that such operators are actually sufficiently localized so that C-star algebra is in here. And again, by Schaaf's result, we know that that one actually is the Toeplitz algebra. So also we have equality here at each place. Okay, so I give you a third or maybe fourth characterization of the Toeplitz algebra, which uses the notion of band operators. And these, let me maybe give you the definition. They were used in some paper by Fulsche and Hager on Fredholm theory for Toeplitz operators on the Fock space. And what is a band operator? So I look at bounded operators on the L2 space. We call this a band operator if there is some positive omega such that MF, Mg is 0. These are multiplication operators by L infinity functions f and g. If the distance of the support of f and the support of g is bigger than omega. So this d means just the Euclidean distance of these sets. So if the support of f and g are far enough apart, then this product should be 0. And the band-dominated operators now is defined as the norm closure of all band operators in L of L2-1. And here are some well-known facts. These band-dominated operators, they form a C-star algebra, and they contain the orthogonal projection, the orthogonal projection P, and they also contain all multiplication operators with bounded symbols. If I take an operator which is band dominated and I cut it off with the Toeplitz projection from the right and from the left, then that C-star algebra here actually contains the Toeplitz algebra. That's rather easy to see, but in fact more is true, and one can show that also these algebras here are actually the same. So the Toeplitz algebra also is the cutoff from the right and from the left of the C-star algebra of band-dominated operators on Cn. That also gives you the Toeplitz algebra.
One question at that point. Maybe it's question to three of you. For you, for Igor, Maximenko, and Grudsky. This definition of band-dominated operator very similar for the definition of, or definition by Simonenko of when he used his local principle. It's the same. It's the same. Yeah, this. Oh, no. Simonenko asked that this product is just compact operator.
Yeah, you may ask 0 or compact. Yeah.
By Simonenko, operator is satisfied to some localization procedure if this product is just a compact operator.
So that may also work for compact, but I'm not precisely sure here. But what I, for example, don't know is whether this is still true for the Bergman space over the unit disk. That might be still true. I mean, this inequality, this inclusion here is still true. So this contains the Toeplitz algebra also for the Bergman space. But whether you have equality, I don't know in that case. I mean, at least the proof doesn't work that way. Okay. So now I want to give you more characterization of the Toeplitz algebra from some other general principle, which is called correspondence principle and was established in a bit different framework of quantum harmonic analysis by Reinhard Werner, who is a physicist. Actually, he's from Hannover, so I know him well. And here I want to do everything in the case where p equal 2, just to make notation more simple, but it works also for different p's. And that's actually part of the thesis of Robert Fulsche's thesis, and maybe you have seen already something, but anyway, so let me explain some things. So here I want to look at the 2 Fock space, and I look at the Schatten-Q class. And the Schatten-Q class is the interpolation space between the bounded operators of the Fock space and the trace class operators. And now I define several Banach spaces. And these are denoted by AQ and A infinity, so Q between 1 and infinity. And it's just a direct sum of LQ and this Schatten Q class. And on this space, I put this norm here. So just the maximum of the LQ norm here. So this is the usual IQ. There's no Gaussian measure here. And the operator, the Schatten Q norm on the operator side. And correspondingly, for the case Q equal infinity, it's just a subnorm and the operator norm. Okay, these become Banach spaces, and these Banach spaces, they carry some group action which come from the action of Cn. And here's the action. It's denoted by alpha set, so I had this notation before. And alpha set of an element here, which consists of a function f and an operator a. It acts on the function just by a simple translation in the argument by set. And as Nikolai already mentioned, on the operator side, it acts by conjugation with these unitary while operators. So that is the action of the shift on the operator side. And they form a group in this sense, alpha set composed with alpha w is alpha set plus w. That's rather easy to check. And now I look at two C-star algebras. So the first one is denoted by C0. This is a C-star algebra of bounded functions. It's a C-star algebra inside L infinity bounded functions. And I consider such functions which have the property that this shift here is continuous with respect to the subnorm. And then I look at C1, which is an algebra of operators on the Fock space, which is the algebra consisting of all operators such that this map here is continuous with respect to the operator norm. And with these two spaces, I define a subspace of A infinity. So this is a space of functions, this is a space of operator, and that's denoted by C. And what's certainly well known is that C-star algebra C0 is just an algebra of bounded uniformly continuous functions on Cn. And also C1 is a C-star algebra, and I will tell you later what it is. And now I want to also put a product, a convolution product on these spaces. So on L1 function, this is the usual L1, so without any Gaussian measure, this is Lebesgue measure, we have the usual convolution. And then I can define a convolution between a function and a trace class operator. And that convolution should be commutative. So f, a function convolution with a trace class operator, is the same as this one, and it is defined as this Bochner type integral. And the result of this will be an operator. Pardon? So this is the Lebesgue measure here. That these are these while operators, and that's an L1 function that converges nicely as a Bochner integral. The result will be a trace class operator. And I can also take a convolution of two trace class operators. The result will be a function, will be actually L1 function. And it works like this. So I take two trace class operators, and I form this operator here inside. U is this parity operator. It flips the sign inside the function. And then that's a trace class operator. And I take the trace, that gives me a function in the variable set. And now if I put them all together, that gives me a convolution on this Banach space A1, which is L1 space plus trace class operator. So this is just a definition. So I take a product of two elements in here. So I just multiply out. The first part here is a function, and this here is an operator. That's an operator. And that's a commutative product and is also associative. And then I can actually extend this product from A1 times A1 to A1 times A infinity. So A infinity was that sum, L infinity plus bounded operators. And via interpolation, I can also get it from A1 times AQ. So AQ is that space here to AQ. So that's an extension in the usual way. Though there's some small observation, if I take f plus a in A1, so f an L1 function, a trace class operator, and g plus b in A infinity, this bounded function, bounded operator, if I take the product, I get something in the bounded uniformly continuous, a space of bounded uniformly continuous function. And here in this space C1, the C-star algebra, which consists of all continuous elements in the bounded operators with respect to this conjugation map W set. Okay, so that's just a very general framework, and I want to explain where's the link to Toeplitz operators. And I want to do this just in the case where p equal 2 and t equal 1 to make things a bit simpler. And here are the relations. So in particular, I can look at the rank 1 projection on the Fock space, which just takes a holomorphic function and evaluates at 0. So that is certainly a trace class operator. It's a rank 1 operator. And if I take a convolution of a bounded operator with this rank 1 projection, then I produce a function. And that function is just a Bayesian transform. So it's another way to write the Bayesian transform of an operator. And on the other hand, if I take that rank 1 operator and take the convolution in the above sense with the function, L infinity function, then up to this factor here, the result will be, it's an operator, the result will be just the Toeplitz operator. And here's what you obtain if you take a convolution between these two rank 1 projection, you get a function, it's just that Gaussian function here. And that connects somehow to Toeplitz operators. And now let me give you an application to the Toeplitz algebra. So here I look at this family of Gaussians, which also in a sense appears in the Berger Coburn theorem. So S is some parameter. And then C1 was this C-star algebra of continuous elements in the bounded operators in the Fock space, just to recall. And here's the characterization. So C1 is the span, the closure of the span of F convolution with B, where F is L1 function and B is a bounded operator. That's another way to write C1. Or it consists of all bounded operators which have the property that if I take convolution with these Gaussians and S goes to 0, then that converges to be an operator norm. Or it is the following. If I take convolutions with this rank 1 projection and bounded uniformly continuous function, and I take the closure, then that's also C1. And since Toeplitz operators are with bounded uniformly continuous functions are just obtained by convolution of this with this one here and an element here, we see that that is actually just the linear closure of Toeplitz operators with symbols in the space of bounded uniformly continuous functions. So C1 is the span of all Toeplitz operator with bounded uniformly continuous functions.
Basically, it's Toeplitz operator algebra.
Yeah, that's a C-star algebra, as you can see directly from the definition, and that tells you actually that's also a C-star algebra. So we recover the result by Shah here. Okay, this was just the result I told you. So from the last theorem, we recover Shah's result, which tells you that the Toeplitz algebra actually is just a linear span of Toeplitz operator with a bounded, essentially bounded symbols, and you take the closure. So here, the only thing I did, I replaced L infinity by bounded uniformly continuous functions, but it's easy to see that if you do that, then these C-star algebras or these spaces do not change. You can always do this. And in particular, we get a new characterization of the Toeplitz algebra, namely the Toeplitz algebra. So this algebra C1 of continuous elements is actually again the Toeplitz algebra. So that is another characterization. It's C1. Okay, so here's maybe just to repeat the result. There's nothing new in this theorem. So the Toeplitz algebra is the linear span of the Toeplitz operator with BUC symbol, taking the closure, and that's that algebra of continuous elements, actually. Okay, maybe I skip this remark because the time is running and tell you a bit about corresponding spaces. So here are the definition again, which I gave you at the beginning. So A1 was L1 plus the trace class operators with some Banach space norm, and A infinity were the bounded functions plus the bounded operators on the Fock space, 2 Fock space. And I explained to you that I have some convolution from A1 times A infinity to A infinity, which came from extending the convolution product on A1 to this space here. And now I can define the notion of a pair or of corresponding spaces. So a subspace D in A infinity, which is of the form D0 plus D1. So D0 is a space of functions in L infinity, and D1 is a space of operators in the bounded operators on F2. This is called a pair if when I take convolutions with elements in the trace class operators, I stay in D. So convolution with elements in trace class operators leave that space invariant. Then we call it a pair. And in this case, we call these spaces D0 consisting of functions and D1 consisting of operators. We call them corresponding spaces. And here's a result on corresponding spaces. So assume that we have a pair. So this is a corresponding, these are corresponding spaces. And then I want to recall that that algebra C1 of continuous elements in the the bounded operators of the Fock space actually is just a full Toeplitz algebra. And then the following things are true. If I take the closure here of this one in this Banach space, then that's also a pair. If I take a convolution from of functions in this space D0 with this rank 1 projection, PC, then I get a dense subspace in the intersection of D1 with the Toeplitz algebra. That stands in here with respect to the operator norm. On the other hand, if I take a convolution of the rank 1 projections with operators in D1, so here in this space, then that will be dense in this symbol space D0 intersected with the bounded uniformly continuous function with respect to L infinity norm. And now the next two are important. If I take an operator in the Toeplitz algebra, and if I take the convolution with PC, then I end up in D0. Sorry, if I find out that this convolution of this operator with PC is in this space D0, then I can conclude from this that that operator actually is in the closure of D1. And on the other hand, if I have an element which is bounded uniformly continuous, and I form this product here, then I end up in the space D1. So that's actually the Toeplitz operator with symbol F up to some constant. So if this happens, then that symbol actually came from the norm closure of D0. And then the last thing is, if I have an alpha invariant subspace inside the bounded uniformly continuous symbol, so this is the shift invariance, then there's always a unique closed and alpha invariant corresponding subspace of operators in the Toeplitz algebra and the other way around. So alpha invariance somehow gives you a unique pair. Okay, so under the alpha invariance, we can, of a space of functions or a space of operators, we have the corresponding spaces and we can use that notation for the corresponding spaces. Okay, let me give you some examples. So for example, if we look at a space of symbols which is inside the bounded uniformly continuous functions on Cn, and I assume this is shift invariant, then I obtain the corresponding space of operators just by looking at Toeplitz operators with these symbols here from D0 and looking at the closure. For example, if this space D0 is just a space of functions continuous and vanishing at infinity, then the corresponding operator space is the space of compact operators, and that's obtained just by the norm closure of Toeplitz operators where the symbols are in C0. Here's another one. We may take the space of vanishing oscillation functions at the boundary. Okay, that should be at infinity, which is denoted by V omega delta. And the corresponding operator space is the essential commutant. It's the essential commutant of the Toeplitz algebra, which is, okay, consisting of all bounded operators such that the commutator is in the ideal of compact operators for all B in C1. So we can also replace L here by C1, then it will be the same space. Okay, so these are some examples of corresponding spaces.
Wait a minute. How do you know that this corresponding space is essential commutant? Or you just obtain some class for which you know that this is essential commutant?
Okay, this is maybe not so immediately. One has to prove. One has to prove it really. Yeah. So it's. I'm not sure whether you can see it immediately. I mean, these maybe are not. So details are written in Robert Fulsche's thesis. Probably have read it, but yeah, it's the one page of calculation.
I see. Okay.
Okay. So by this method, we obtain the result by Israelowitz and myself very easily. So here we had this theorem that an operator is compact, the bounded operator is compact, if and only if it is contained in the Toeplitz algebra and its Berger transform vanishes at infinity. And that is just a direct consequence of the correspondence principle, this theorem which I just told you. And the fact that C0 is the corresponding space to the compact operators. So if A is a compact operators and the compact operators are in the Toeplitz algebra, then if I use part C of the theorem, then I obtain that the Berger transform, which is just this convolution here, is in C0, because C0 is the corresponding space of the compact operators. That is part C of the theorem. And on the other hand, if I have an operator in the Toeplitz algebra, and I find out that the Berger transform, which is just this convolution, is a C0 function, then the theorem tells me then this operator has to be actually compact. So that's a very simple proof using the correspondence theory. Okay, maybe my time is running. I will skip this, but still almost at the end, I will still tell you the question. So in the definition of the corresponding spaces, we have two spaces. D0, which is a space of functions, of bounded functions, and D1, which is a space of operators. Now I assume that this is, we may assume that D0 is, for example, a shift invariant C-star algebra, so it's more. And then the question is, if it's shift invariant, then there is a unique corresponding space of operators. And you may ask whether then this space of operators also is a C-star algebra. So whether this C-star property of the function space somehow translates to the operator space and maybe the other way around. So this is the question. If this is a C-star algebra, is this a C-star algebra as well? And if you look at our examples, that doesn't look very unlikely. So for example, if I take BUC as D0, then the corresponding space is the full Toeplitz algebra. So that's a correspondence between C-star algebras. Or if I take a C0 function, continuous functions vanishing at infinity, then the corresponding operator space are the compact operators. So it's also a C-star algebra. Or if I take the vanishing oscillation functions at infinity, then the central commutant also is a C-star algebra. So in all these examples, that's actually true. Okay, so these are all alpha invariant C-star algebras. And here, so you may ask whether there is a generalization of Scha's result. So Scha observed that if you look at the full Toeplitz algebra generated by Toeplitz operator with all L infinity symbols, then this C-star algebra is just the closure of the Toeplitz operators with the corresponding symbols. So the question is, for which subspaces of L infinity does such a thing happen? That the closure of the linear span of Toeplitz operators with symbols in this subspace S actually is an algebra, a C-star algebra or a Banach algebra if P is not equal to. And here's one result which tells you that that may happen rather often. So if A is a shift invariant C-star subalgebra of the bounded uniformly continuous functions, and also if it is U invariant, U was that operator here, which flips a sign in the argument, then it's true for all P between 1 and infinity, that actually the closure of the Toeplitz operators with the symbols in that shift invariant U invariant C-star algebra, that closure, linear closure, coincides with the Banach algebra generated by all these operators. And so that somehow generalizes Scha's result, which holds for all these PUC, or if you want L infinity, to such shift and U invariant subspaces. And to my knowledge, so this is a result by Robert Fulsche. It's not clear whether you really need that assumption here, but in his proof he needs it. So it might be even true that you can omit this assumption here. Okay, so I'm almost at the end. So the proof is based again on the correspondence principle, which I told you. This is my last slide. Here's one example of such a shift invariant algebra, which you may ask whether that's a Toeplitz algebra or not, and that's the resolvent algebra. And the resolvent algebra was somehow introduced by Grotlik and Buchholz in the framework of quantum mechanics, and it's a replacement of the CCR algebra, canonical commutation relation algebra, because this algebra has some better physical properties, some kind of invariance properties which the CCR algebra does not have. So they look at this algebra as an algebra which encodes the canonical commutation relation and use this instead of the CCR algebra. And in the CCR algebra, you somehow have, you take the unbounded operators which fulfill the commutation relation and you turn them into bounded operators by plugging them into the exponential, so to say. And here in the resolvent algebra, we take resolvents of the unbounded operators to come from unbounded to bounded. And there is a Fock-Bachmann representation of this. This resolvent algebra is the C-star algebra, which is generated by resolvents of Toeplitz operator, where the symbols are this imaginary, linear functions here, imaginary part of that inner product here. And these are generated by these things and by the inverses. Lambda runs through C minus IR. And that resolvent algebra does not come to us as a Toeplitz algebra, because these resolvents of Toeplitz operators are not Toeplitz operators in general. But you may still ask whether this actually is a Toeplitz algebra. You know the CCR algebra and the Fock-Bachmann representation is actually a Toeplitz algebra. It's generated by Toeplitz operators. And the question is that also true here? Is that R actually a Toeplitz algebra? So is there some symbol space in L infinity such that this algebra really is generated, is a C-star algebra generated by Toeplitz operator with that symbols? And the answer is yes, because that's an alpha invariant, it's a shift invariant sub-algebra of L F2. And the correspondence principle, so that just follows from this action of the unitary while operators. So they act on resolvents in that way here. So they take a resolvent and turn them into another resolvent. So the correspondence principle tells you, yes, it's a C-star algebra generated by Toeplitz algebra, by Toeplitz operators with some symbols in BUC. But the question is, what symbols are these? So what is a good description of this space S here? So that's just an example to which the last theorem applies. And here maybe in the last line is the description of the CCR algebra as a Toeplitz algebra. It's actually the C-star algebra, which is generated by the unitary while operators. And the unitary while operators themselves are actually Toeplitz operators with bounded symbols. So it's really a Toeplitz algebra. Okay, so that is all I wanted to tell you. Here are some references. This first one is, if you're interested in the resolvent algebra, is the corresponding paper. It's a bit physical. And then there are some results in this paper here with Robert Fulsche on the Berger Coburn theorem. And Robert Fulsche wrote some paper on the correspondence theorem for the p-Fock space. And the original paper, which contains this for the Schrödinger representation, is actually this old paper by Werner on the quantum harmonic analysis on phase space. This has most of these ideas. Okay, so that's all.
Thank you.
I apologize for using a bit more time than I should. Thank you for listening.
No, that's completely fine. Very nice talk. Thank you very much. I have a few questions, and then maybe other people will have questions. How did this fascinating idea appear to use this quantum harmonic analysis?
How this appears in the original paper?
No. In your work with Robert.
Okay, so with this quantum harmonic analysis, you can somehow try to generalize results which you have in harmonic analysis to operators. For example, the Wiener approximation theorem. On these kind of theorems, you may ask whether you have an operator version of this. And I think such things are some motivation to look at this from the operator side. And as for me, as I said, Werner is a colleague of mine, and once we had some common bachelor or master student actually, and we had to try to find a topic which we both somehow like. And he did this quantum harmonic analysis, and we did Toeplitz, and then I looked at this paper, and he had very interesting theorems which give you compactness, and I didn't believe them. And then Robert Fulsche tried to translate them to the Toeplitz world, and so that's somehow the connection.
Okay, so basically it was the effect of Hannover University that both of you are working.
Yes. So it would be, yeah, but so it seems to work if you have a lot of symmetries.
Yes.
Yeah, but it produces a lot of theorems and or characterization of the Toeplitz algebra, which could be also conjectured for Bergman spaces, for example, or spaces where you have a lot of symmetries which replace the shifts. But in that case, that machinery does not work, but you still have the conjectures there. So
yeah, well, because you need some kind of convolutions.
yes, I mean you still have these unitary operators.
Yes, definitely. Yes.
Certainly, but then you lose commutativity, and then things become a bit strange.
It's possible question, Kola.
Yes, sure.
So my question is following. I see that all is ready for application of the limit operator theory for the investigation of the Friedbolmers. What do you say about this?
Yeah, there are some results by Robert Fulsche and Raphael Hager, and they studied this limit operator approach to calculate the essential spectrum of Toeplitz operators or elements in the Toeplitz algebra, actually. And I think they did this first for this cutoff BDO space, so the cutoff of the band-dominated operators. And it's, I think, very similar to the situation of infinite matrices. So they have the operator, and then they look at these. Okay, let me go back in the slides. Okay, maybe here. So they look at they take an operator and they look at this function here, and they show that this is actually already done by work by Suarez, that if this is from the Toeplitz algebra, then that function here extends to a compactification of Cn, and the boundary values of this are then the limit operators, and the essential spectrum of the operator A then somehow is obtained from the union of the spectrum of the spectra of the limit operators. Something like this they prove. So it's very similar to my understanding to the case of infinite matrices.
Is not conjugation here?
Oh yeah, there's something wrong. Yeah, thanks. There should be a minus sign here.
Okay, this is the way to see limit operator in this context.
Yes, yes. It is very interesting because the limit operator work very effective in the many other problems, and then solve the limit operators. Maybe this is a new area application of the limit operators to these problems.
Yeah, this is actually a very, very good comment, and also it's I completely agree with you. So when we looked at this first, there was this work by Suarez, Daniel Suarez, and he already had all these ideas of extending this to the boundary and looking at the boundary values, but he could not fully prove he only got some kind of inclusion of the essential spectrum in some set. He could not prove equality of this. And then Raphael Hager came, and he was working on limit operators and these kind of approaches. He came from Marco Lindner, and they have a lot of machinery and techniques. And he managed to put this together to improve actually the theorem and get easier proofs of that. So that these ideas are very useful. Yeah, I agree.
Of course, I know this. Other question. There is some physics interpretations, the spectrum, essential spectrum, and other things of the Toeplitz operators in the Fock spaces to the some question of the mathematical physics, quantum mechanics, and the field theory, and something like that.
Whether there's an interpretation?
Yes, the physical interpretation, the spectrum of the Toeplitz operators.
Yeah, I'm not sure whether I can answer this in that general formulation. I mean, certainly Toeplitz operators are very, especially on the Fock space, very closely connected to quantum mechanics and physics from the commutation relation and from this quantum harmonic analysis. And this spectral yeah, I mean, there are certainly there are relation to the Landau level sets and so on, but I'm not sure what you precisely mean.
Okay, thank you very much.
Wolfram, can you return to the definition of band operator? This slide.
Let me see.
Band, yeah.
Oh,
Band.
yeah, this was earlier. So here.
Yeah, Volodya, I'm very glad that you are here. So my question remains the following: if to change this definition, so this product is just compact operator, it will be exactly in the spirit of Simonenko work. How the theory will change? What we may expect if we will have not zero but compact operator?
So I suspect that probably Robert Fulsche tried this. I think he mentioned this once, and I guess if I remember correctly, then nothing will change. So that will be a weaker condition.
Yes, weaker, yeah, sure.
It will be a weaker condition, but probably you still have equality here, I would assume.
As far as I remember, in Robert Fulsche, it's still stated like an open question in his thesis.
It depends. Once he stated this, and once he told me that he thought about this. So I never tried this, but it's a very natural question, I agree.
Yeah,
I would assume, I mean, what happens here, all these algebras you generate, in the end, they are the Toeplitz algebra.
Mm-hmm.
So at some point, we try to find algebras which are larger than the Toeplitz algebra, and you still have the compactness characterization.
Mm-hmm.
So further extend this result by Suarez. But it turns out that all these constructions you come up with in the end give you the same thing.
Mm-hmm.
So that in some sense that might be the largest one.
Wolfram, again, one question, sorry. Some perspective to use this machinery in the Bergman space case?
Yeah, this is a very natural idea, and I think this is what I told Robert Fulsche after he did this for the Fock space.
Yes.
But it's
what is the main
not so easy. You can do some things. So, for example, instead of the shift, you take a simple rotation in the disk.
No. Instead of shift, you can do this standard Möbius.
Yeah, but then you lose commutativity. Then it becomes complicated. So if you just take a rotation, then you can certainly do things. But that's a rather maybe not so interesting.
No, it's not so good idea, because by rotation you cannot approach the boundary.
Yeah, you should use somehow all symmetries of the domain in this approach.
Yes. Yeah.
But I think he looked at this also. Raphael Hager looked at this, and I don't think there was much outcome. So this seems to be. This seems to work well for the Euclidean setting, and maybe you can replace the Euclidean setting by some group, by some Lie group, maybe some nilpotent Lie group. I assume maybe Heisenberg group, and change the convolution in that sense. But
the non-commutative convolutions.
Yeah, I think some people work on that. But I'm not aware of a meaningful extension to other domains than CN. So I have to say that.
Okay. Well, I did some work with my student, Rafael Trujillo, something about convolutions on Heisenberg group. But it was very long ago. So please, other question? No questions. Wolfram, thank you very much. It was indeed very interesting talk.
Yeah, thank you very much for having me and listening.
Yes.
Very happy to be there visually, but I hope we will meet next time in person.
Well, who knows when?
Yeah, who knows? So now they start with the vaccination.
Yeah, yes.
But it will take probably a year until that has some effect, I'm afraid.
Christian, are you here? Your talk is next.
Yeah, I'm here, of course.
Okay, so next Tuesday will be your talk.
Okay, thanks.
Okay, so thank you
Okay,
very
so
much.
thank you to everyone.
Nice to see you,
yeah.
Wolfram.
Yeah, see you. Bye, Raul.
Thank you,
Bye.
Wolfram.
Bye-bye.
Bye bye.
Bye. Take care.
Take care.
Yeah.
Yeah, thank you.